Good afternoon, everyone. As Charles has said, my name is Shane Fenton of Wain Morehead Architects. We were engaged to carry out a building energy assessment of the proposed building, which Joseph has, I've no doubt gone through in great detail, following completion of the works. We also developed a BIM model for the project from a point cloud in combination with a point cloud model that was provided to us, and from the design drawings provided to us by Joseph as well. And that model was used. The model was used as the basis for our energy assessment, but it was also used to generate the schedules and volumes that Sarah has used in her life cycle assessment that she will cover after this. So a deep assessment was carried out for the building by IHER Energy Services. I won't dwell too much on it as we didn't carry out the assessment, but the original rating for the building is a mid-G. Following the renovation, the BER of the completed project based on default values was F, so not a huge improvement from a G to an F, just one band. And that is largely down to the default values for the age of the building and the type of the building, where it falls into in the deep assessment. And I suppose you can see the amount of work and detail and everything else that has gone into the building, and to only go from G to an F, which is perfectly acceptable under the deep methodology, is not very good. It's quite poor in truth, you know. The BER based on calculated values, which will be the actual values in terms of bridging and the actual windows and no default values, improves to C2. I think you'll see later on that it's quite, even from the specification and the actual finished product, is much better than, well, what we perceive to be a C2. Deep in itself is more of an asset rating tool for comparison between buildings and to determine the primary energy of your building, rather than a design tool to really reflect the performance, to reflect performance levels and comfort levels of the building. There was also possible future changes considered, PV panels and the installation of a heat pump. And both of these will bring you up to NA3, which is where your assets come in. Those future changes are separate and not cumulative. So if they were both considered together, it would no doubt be an A1. You can see the space heating, water heating, and renewables are all very, very poor for the current dwelling at a C2, and this is because there are no renewables, and because the space heating and water heating is electric, and I suppose the deep methodology doesn't really consider electric as being the most efficient form of heating and providing domestic hot water. In fact, we've an A1 rated passive house dwelling in West Cork that achieved an energy rating of 10 kilowatt hours per meter squared, and it still has those red very poor next to the space heating and water heating under the deep assessment. So we carried out an alternative assessment using PHPP software, which was developed by the Passive House Institute, to get a greater understanding, I suppose, of the actual performance that would be given by the building relating to the fabric and following the retrofit. So what is PHPP? This is an overview of the PHPP inputs that you require. Many people think that the PHPP software is just for passive house dwellings, but it's very useful for all building types where we are working with existing buildings, and where we are working with existing buildings, we have the Retrofit standard, which is a relaxed version of the passive house standard. The passive house standard requires extreme levels of air tightness and very low energy performance, and it promotes very high comfort levels in buildings. And as you can see in the graphic shown on the screen, there's an awful lot of input and criteria that feed into the overall calculation. So what we did was we assessed the as-built construction, and then we, through a bit of over and back with Joseph, then we reviewed the project to see what would have been required to actually bring it the next step to the Retrofit standard. So the Passivhaus planning package, as I said, it's a building energy modeling software, and it uses a fabric first approach rather than an asset rating system to measure the building performance and comfort levels. And what that means is that it's really focused on your building envelope, including your windows and your G values and things like that, and your ventilation systems to ensure that you can achieve maximum comfort levels in your buildings. And there's no amount of renewables or no amount of efficient heat pumps that will get you Passivhaus certification if you don't meet the basic criteria of having a heating load that is below 10 watts per meter square and a heating demand that is below 15 kilowatt hours per meter square per annum. Some of the key factors that influence your performance, your building envelope and your specification, your orientation and your shading, your air tightness, ventilation, climate. And as I said, PHPP is not only for use in new Passivhaus buildings, but for the refurbishment of existing buildings where we have the Retrofit standard. So you have two means of achieving Retrofit, and as we know, Retrofit can take it's all shapes and sizes. You have two means of achieving Retrofit, and these were developed separately to account for these different building types. Where you have your energy demand method, and the primary target of your energy demand method is to reduce your energy your demand down to your heating demand down to 25 kilowatt hours per meter squared per annum, and achieving your target air tightness. Where your component method, so if your building doesn't lend itself to that, and where you might have to go through extreme levels of insulation to achieve those levels, to achieve that energy demand, you have the component method. As it says there, is if the existing design does not lend itself to achieving the target energy demand due to the orientation. Maybe it's a north-facing building and you're not getting solar gains, and it's not something that you can, if you're working with an existing building, it's not something that you can redesign where you say, okay, well, I need to get in more gains. You might be able to get some more additional gains with some new windows, but often it's not possible. And in the case of this building that we're looking at, it's got a very short frontage. It has two generous sized windows on the elevation, on the main elevation, but there's significant shading from adjacent buildings, and there's nothing you can do about that. I suppose key factor of Retrofit is that the target performance is dependent on the climate zone, whether it be the component method or energy demand method. It's dependent on your climate zone, and whether that be cool temperate or warm temperate, etc. And the backstop U values are higher if you are working with an internally insulated building, which we are here. So this is your performance criteria for your component method and for your energy demand method. And notwithstanding that, you have a target air tightness level, and your N50 of 1 air changes has to be achieved to meet any of your Retrofit standards. So you can see that in your component methods, there's significant, or there's a lot of criteria that you have to meet if you are going that route. Whereas your energy demand method is effectively air tightness and your max heating demand. And you can see there in your, I suppose you can see that in your cool temperate, which you have 25. So the two climate zones, which I'll cover later, are covered in Ireland. It's generally cool temperate or warm temperate, and it's the difference between 25 and 20 kilowatt hours per meter square per annum in context of Retrofit is quite significant. And if you're already at the limit of what you can do, whether it be pumping your cavities or external insulating or whatever the case may be, it's quite a significant jump. But for this project, we're focused on the internal insulation criteria, which is highlighted there, and they're your backstop U values for your internally insulated walls. So interesting. So as I said, PHPP is climate specific, and interesting for this project, we're kind of considering two climate zones. So PHPP has I think there's six data sets that come as standard. So the nearest data set to our project would be Dublin Airport, and that is a cool temperate climate zone. But at WMA, we always consider local site-specific climate data in the project, as there's a significant difference in the performance, and climate criteria across Ireland generally can differ by up to 45%, which will have a significant impact on the performance of any building. But the location for this particular project is considered to be warm temperate climate zone from the climate data that we generated due to the heat island effect, where you have urbanized areas experience higher temperatures than outlying areas such as Dublin Airport. As you can see, there's a significant difference between the backstop values between both the cool temperate and the warm temperate climate zone. So if we were going with by default values, we'd have to insulate all our walls to achieve 0.35 watts per meter square, watts per meter squared U value. Whereas the backstop for our actual location is 0.5, and that is extremely that's a significant thing in retrofit, particularly when you're internally insulating and you're worried about in a building like this, where the more insulation you put on, and obviously it's having a big impact on your usable floor area internally, and also it'll also have a huge impact on your window specification. There's a as Joseph's probably alluded to already, there's the high specification of windows gone into the project, but if it's considered on the built-in cool temperate climate data set, they wouldn't actually meet the criteria. But because we've done our local climate data set, it does meet the criteria. The difference between 0.85 and 1.05 UW install is very significant. So when you are doing your calculations, so they're the key criteria, or that you will find you'll be fighting against when you're working with your Retrofit by component method. So this is some of the results, a graphical representation of the results as built. As expected, there's a demand control ventilation system gone into the building, which accounts for most of the losses and significant amount of losses, and the walls. The windows are high specification. The roof is well insulated. The floor is well insulated. So obviously the walls and the ventilation are taking up the slack, I suppose, of the losses. And you'll see in the bottom left-hand corner, you'll see that your window breakdown with your gains and your losses, and our windows they're probably around neutral and probably gaining slightly more than they're losing over the course of the year. But you'll see the shading breakdown in the bottom right-hand corner. So what we did was we 3D modeled the building and 3D modeled the context all around the building, and you'll see that the amount of shading is extremely significant, and particularly in winter, where your southern windows are being shaded by 62%. So there's only 38% solar gain that would be available actually getting into the windows. So that's having a significant impact on the actual performance. And again, is dictated in part by the local context and actual horizon elements, but also by the individual climate file or data set that you're using to assess the building. So as I said, we were looking at a couple of variants, and we looked at our as-built condition, and we considered a condition with an ELAN Compact P for ventilation, and also what improved measures we would need to get it to Retrofit. And in fact, the only two things we need to do to get it to Retrofit, when assessed under local climate data, which is what we want to be talking about from kind of here on, is put in an MBHR system. And that's for comfort, I suppose, really. Then the Passive Institute insists that you have an MBHR system, so that you're supplying mechanical ventilated heat recovery system, so that you're supplying warm air rather than air at whatever the outdoor temperature is on a given day, much more controlled internal environment, and your improved air tightness, which would be one air changes. So both of those criteria, if you have both of those performance criteria, this particular building would achieve Retrofit by the component method. Retrofit by the component method as it's built. And interestingly, the performance that you have here on the screen, the heating load and heating demand, if we had the Dublin the data, or if we had the building based on Dublin Airport data next to it, it would be 20% higher. So even between Dublin Airport and the actual location for this project, which isn't that far. I mean, they're both in the Dublin area. They're not that far away. It's a 20% performance gap is the difference, which is which is very significant. And if the building was to be assessed using the energy demand method, you'll see the dashed red line is where your energy demand would need to be. So you can imagine, you've seen all the measures that Joseph has gone through to get the building to a level. What extra levels you would need to get your energy demand down to 25 would be significant, extremely significant, and would likely lead to other issues such as hydrothermal issues or very little usable space left over. And our primary energy reduced by 46% between the as-built and the actual standard being brought to Retrofit. That is primarily because you're using a heat MVHR system and a heat pump, and you've better air tightness, which is bringing your PER down by 46%. So this is a comparison of your by achieving your Retrofit standard by the component method, and where we are, and what the backstops would have been based on Dublin Airport data, and what the backstops would have been based on the local climate data. So these are the values we'll focus on. So you can see that, as we said earlier, the internally insulated walls would have had to achieve 0.35 or better to be considered to achieve Retrofit by component method if we were using Dublin Airport data. But you'll see the lighter green color is the criteria based on local climate data. So we're in between. So we have achieved it based on local data, but not achieved it based on Dublin data. And the same goes for our windows, including the doors, and our windows on their own. So the specification of the windows would have to be much, and the door, in fact, would have to be much better to have achieved Retrofit, based on your Dublin Airport data. So some of the key takeaways from what we assessed is that the as-built condition assessed is a extremely high form factor. I know Joseph has covered form factor already earlier, but our form factor calculation came in at 5.15, and there's a few reasons for that. One of the reasons is the extension that has gone onto the dwelling has a high surface area relative to the treated floor area, and in Passive House we're measuring externally as well. So we're accounting for the really well insulated ceiling is contributing to your form factor as well, and the extension that has gone to the rear of the building has quite high walls relative to the internal floor area that you're getting. So that's a huge contribution. From a numeric perspective, if we just don't consider design for a minute and you just consider numerics, if that had a flat roof on it, which would reduce the roof area, it would reduce the two of the wall areas, it would have a significant impact on your form factor. And another component, I suppose, that's having a major impact on the form factor is the light well. And the light well isn't something that we often find omitted from the energy assessments. You'll find that the roof light will go in, but the shaft around the windows won't go in, or something's missing, or it's not considered. And it's a vital thing to consider, because actually when you actually fold out those areas, those light shaft walls are accounting for 2.5 meters squared of your envelope. And in some buildings, you might have quite a few of them. If you're insulated on a flat ceiling, and you have your roof windows, so they can be quite significant, and they are also adding to your form factor of the new building. And in this building, because we've got quite good timber frame walls, which are quite heavy stud, which are at 220, I believe. You've got existing external walls, which have all been insulated internally, which have made your walls thicker. The external walls are actually counting for 25% of the footprint of this building, which is extremely large relative to the actual size of the building. So if you had which is because we're measuring to the outside for Passive House assessments, and that's contributing to the high form factor as well, because your treated floor area as a result is being compressed. So if your treated floor area was even 1 meter or 2 meters squared bigger, it would reduce that form factor quite substantially. It's difficult, almost impossible to achieve Retrofit by energy demand method on small buildings, and it could lead to over specification and over insulating of external walls, which in turn can lead to loss of usable space internally, could lead to hyperthermal issues that aren't being considered, etc. But Retrofit can be achieved using the component method and by assessing the building with a local climate data set, and which can be verified for the PHI for certification purposes. And there's a difference of 20% in the predicted performance in this project between both data sets. And you can consider even further if the building was in a different area, a location in Ireland, it can be quite different as well. The Retrofit threshold for internally insulated walls was 0.5 for the Dublin Airport data set, but 0.35 for the local climate data set. And as I say, only a couple of miles apart in real terms, and it's quite a difference, quite a substantial difference in your backstop U values. I think it's critical, and the overall context of retrofit in Ireland is critical that the appropriate solutions are considered for the building retrofit that responds to the building typology, the climate, orientation, and shading, rather than achieving a rating based on assets. The climate, as I said, the climate characteristics in Ireland can vary by up to 45% countrywide. So you can imagine if you have one building down in West Cork and you have one building in the Midlands, let's say, where it's much colder and there's much less solar access, the design response would be and should be quite different. So we shouldn't be treating all our buildings the same. There's a specific design solution for every project. Say depending on its climate, its typology, its orientation, and shading. So that's it from me.
Thank you very much, Shane. Shane, do you want to stay for the next talk?
I'm actually under pressure. I've a workshop for my TUSD students at 2 o'clock. So I need to run, unfortunately.